Hello. First of all, yes, okay. Okay. So, I will say sorry first because my slides, there are some in Portuguese and some in English. I hadn't time to translate. So I will talk about my project in my postdoc that's running for axon-like particles with top quarks at the high-end frontier. I am from Sprace. I will explain a little bit what we do there. See here. And already asked you. Um, so I'll talk about the Sprace, the institute I work, about the standard model. I mean, it's a very basic presentation. I know a lot of you are experts, but I don't know if there are some people outside the field, but I will try to give an overview of what we are doing, about the experiment, and about how we are processing and analyzing the data from SMS and from LHC. And this is our building. This is the same building at IFT. I think some of you know because of the events that ICTP that occurs here. We are located at the first floor on the ground floor here. It's the same location of the data center. That's the grid UNESP that attends all the UNESP community. And also we have a tier 2 from LHC. That's a computing site that store data and also process data for the whole LHC computing grid. This is just an old picture of the data set, the data center. So I'll talk a little bit about this Sprace, just to people who don't know. So the Sprace is a acronym for the São Paulo Research and Analysis Center. And we participate in the CMS collaboration, the CMS experiment, that's the compatible solenoid from the LHC. There we develop beyond standard model physics, as well as heavy ions. We have the two groups working together. And we also operate the tier 2 from the worldwide LHC computing grid, the tier 2 BR Sprace. And also we have some working instrumentation physics for the SMS experiment, also with the private sector, especially for the phase 2 for the SMS detector. And our group also promotes the international masterclass every year. That's an outreach program for high school students and professors from the high school and also some graduate students. So this is our team. I think some of the faces you know. This is me. This is our professors. Thiago is my supervisor now from the postdoc. This is my colleagues. And there are more people. There's more people than this, but this is just people that work with us in everyday basis. And I'll talk now a little bit about physics. So starting with the standard model, of course. This is a just general picture. I believe every you people here know most of this. So this is what constitutes everything we see, and also as well some things we don't see directly. But I will not give you entering details. I'll show you this you here to state the facts that it's not perfect. Of course, we have some problems. Let's say that's open questions in the standard model. And one of those open questions that we are trying to solve is the dark matter problem. So the dark matter comprises about 27%. This percentage changes all the time. So if you're any specialist in the crowd, people don't judge me. But this around 27% of dark matter that comprise the all dark matter energy density of the universe. And only the 5% is the rest of the things we know, like stars, galaxies, planets, gas and dust and stuff, neutrinos as well. And we have dark energy that I will not talk about, but it's a complete different field. But yeah, what we are aiming here is to study the dark matter, especially that dark matter that we think we can produce that in colliders. Like, because we have three kinds of detections for dark matter. So we have the direct detection, the indirect detection, and collider searches. So each of these kind of searches has one way to produce or detect dark matter. For example, if you are interested in produce this dark matter in colliders, we want to smash standard model particles into some kind of new physics, and then look for a dark matter constituent, like in the final state. Of course, maybe this dark matter would not be visible because it would escape the detector, and this is one of the kind of signatures that we are looking for. Of course, we have the direct detection as well, that we are looking for the scattering from standard model and dark matter particles, and also the indirect detections that comes from satellites or some ground experiments as well, that we can look for fluxes of dark matter coming from the space. Okay? So, talking about specifically about the colliders, this is a picture from the region of the LHC is located. Of course, the LHC is underground here. Here we have the interaction points where is located the four experiments, the Atlas, LHCb, ALICE, and CMS. Here we have the frontier from France to Switzerland. And most of the centers and labs and stuff here it's located here around these interaction points. But of course, we have other centers across all the ring. So this is some parameters of the LHC. Right now, we have the nominal energy of 6.5 TeV. For ions, we have 2.56 TeV. The collisions now, it's not 13 TeV, right? I think it's 13.6 TeV right now, not wrong. And the collisions per second is more than 1 billion. If you are, the LHC, for example, it's running now. We are taking data from the run tree, and we are thinking about this. We are seeing about this number of collisions per second. Of course, we are not storing all of the data because there's a lot of triggers, a lot of filters, and a lot of stuff going on. But yeah, I mean, the collision itself and the bunch per proton generates a lot of collisions, a lot of pileup, a lot of stuff from the different experiments. And of course, a lot of data. So this is news from today. I just checked my social network, so you can see 17th of December, because CERN just hits 1 exabyte of data. It's like, it's 1,000 petabytes, I think. So you have gigabyte, terabyte, petabytes, and you now have 1 exabyte of collision data. It's not Monte Carlo, it's just like collision real data. Okay? I think if you include Monte Carlo on this, it will be like double, triple of that. So this is you can check here if you want to see the news, but it's just because I was talking about this and then I just saw this news and I think it would be nice to show. So, more about LHC. Sorry for the people in the audience that already know this, but it's just like general talk, like I said. But the whole tunnel, it's about 27 kilometers. Those blue stuff that we see usually are the magnets that will curve the trajectory of the protons. Of course, we think about LHC like a perfect circle, but it's not, right? Because in practice, we need to curve the trajectories. We need to accelerate the particles, curve, accelerate, curve, accelerate, curve. So that's why it's not a perfect circle, but more like a octagonal, like this. So the tunnel itself, it's underground, of course, and here you can see the points. The experiment we work, it's the CMS. It's a general proposed experiment, same as Atlas. And also we have ALICE and LHCb, that ALICE is more focused on heavy ions physics, and LHCb is more related to decays and flavor violation physics. So, like I say, this is the actual the design of experiment, because of course the civil engineer is not easy. This is a slide I take from my former advisor, because it's nice to see here. So you can see also that the ring itself, it's not totally plain. We have like 1.4% of inclination here from the ground. The diameter of the tunnel is 3.8 meters, and we have the caverns from 50 meters in each point, interaction point, like the CMS, the Atlas, the HCB, and the Alice. Okay. So like I said, you see there's an accelerator part, and then there's the curve, the beam part, like over and over again. This is just to illustrate that the actual ring, the main ring, is actually the final part of a process, because we need to accelerate these protons and give energy to previous steps. So we have like this, and this also, it's you can see like some kind of history of the LHC, because you can see here in 1959 where the first ring was constructed, and then you can accelerate here, and then you have a beam line here to a more energy, and then from the former lab tunnel here, sorry, this SPS, and then of course the LHC, you can see the energy that's gaining on until you reach the 70 eV. So 26 eV, 40, 50 TeV, until you have like the 70 eV. So it's not like straight to 70 eV being, you need those steps that the protons to gain energy. So this is the experimental work, the CMS experiment. I'm now in the postdoc, I'm part of the collaboration. Before doing my PhD, I was just doing phenomenology, but my former advisor was from this experiment already. And then, just to you don't know compact muon solenoid, is because it's a solenoid, of course. You have like a magnetic field from 3.8 Tesla. It's compact. I mean, from the space that you would need to construct this, it's very compact, especially if you compare with another experiment of the same kind. And we are focused on muons. The precision of this MS to muons is higher than the other experiments of the same kind. This is a 3D view of the experiment, and also a scale here with the person. So you can see here the tracker, the calorimeters. Here's some parameters. I mean, the total weight of 14,000 tons, total diameter of 15 meters, the magnetic field, like I said, 3.8 Tesla. And here you can see the parts of the detector. I mean, the electron calorimeter, the hadron calorimeter. Each one of these steps is specialized to detect one kind of particle. I mean, of course, the electrons or the hadrons, and the muon calorimeter here in the outside. So here's another view of the experimenter, from the experiment. Here you see the tracker, the silicon tracker, and here you can see like a trajectory of a particle, for example, from an event. So this blue line would be a muon that you can see that curves here in two different ways because of the change of the magnetic field. This is the solenoid. This is the electron calorimeter, the hadron calorimeter. You can see, and here when you have some deposits of the energies here, we can read this like in the way. I mean, of course, the data set, but not like these beautiful like we see here in those images. But that's the main idea, right? So we check the deposit of the energy in each of the calorimeters, and then we reconstruct the whole event. This is a video that I don't know you try to. There's a way to. So this is just a outreach video, just to because it's nice to see the CMS working. So you can see the beam and the whole calorimeter is working like with a real event, let's say. I think we have time. We have time. So, like you see, so this is just a 3D representation of an event inside the beam and inside the experiment. So here is when the collision occurs. You are inside the tracker, and then we can see like a lot of tracks going on from the same event, and all the deposits of energy. And of course, depending on the space, the phase space that you are looking for, we have more or less sensibility. Of course, in the radial area, we will have like more sensibility than the rest of the experiment. And I think that's it. Pass. So the LHC works on runs. I think some of you know. We have the run on in starting 2011. Where's the light here? So in 2011 we have the run on, and then we have the discovery of the Higgs boson, and then we have the run 2 with more energy, and then we have a long shutdown again to upgrade the detector and the experiment, and then now we have the run 3. So we are here in the end of the run 3. So the run 3 it's predicted to end in July or June from the next year, I think. And then we have again a long shutdown to the install of the high luminosity LHC. That will be I mean, the same experiment, but the luminosity, I mean, the number of events will be way higher, up to 5 to 7 times the nominal luminosity. And it will run the run 4 until, I don't know. So, but the provision is to start in 2029, and then we will have the next run. But I mean, the data from the run 3 is already been taken and already being analyzed. So we have already papers coming from this data taking that's still running. So pay attention to the next in the next publications. So talking about again from the dark matter perspective, when we are looking for dark matter, we are usually not expecting to see anything from the detector. Of course, the detector is made to observe standard model particles like muons, electrons, hadrons, and the dark matter is none of that. So what do we expect here in the detector itself? It's something that we can identify, like a jet or some particle, and a missing energy. I mean, a missing momenta here that an event would be. This would be like ideal event, right? So you see like a lot of things in one side, and you see nothing from the outside. But of course, a lot of events can mask this kind of scenario, like I was discussing with Camilo, for example, that we have like systematic errors, you have like neutrinos, you have like some things that can mask this, so you need to know your statistics very well and your backgrounds very well to identify some missing event as a new physics or something like this. In my case, what I'm looking for is axions. So axions is one of the plethora of the models that we can have for dark matter. The motivation, the original motivation for axions is to solve some of the QCD problems. But of course, the problem itself that the axions try to solve, like from the paper from P.K. Quinn, it's not. I mean, the parameter space is well restricted, but even though that motivates other models that we call the axion-like particles, that there are particles that similar to axions, but not exactly the original axions that was proposed for C.P. Quinn from solve the CP problem. And here's some just a diagram for. In this example, we call these double top productions, like you have a top and top and top pairs, and one of these top can violate flavor and decay two axons here. And this will be a single top production when you have this event here decaying two axons that will be missing energy, and then here we have like a jet or something from these axons. This is just an example. You have more diagrams that can generate this, just to illustrate what I'm talking. For example, in this kind of decays, we could have like displaced vertices. I mean, this is the tracker, like I show you, and these we have like points when the particles would, for example, if those invisible particles would be produced, and then we could decay like in a displaced location, not in the center, in the collision center. So you can identify this with the data, because here in the silicon tracker, in the center region of the detector, we have a lot of sensibilities and a lot of time resolution to identify where the particle is produced compared to the center point of the interaction point of the experiment. So what we are doing, actually doing there, is taking data from the CMS. So the CMS is now, for example, in the run tree producing data, storing data. So we take those data, we develop triggers and analyze the triggers. So the triggers, I don't think if I explain that, but just it's kind of a filter in the very rough way. So that will say that if the event, if I'm seeing that one event, that event will be recorded or discarded. So kind of, and that if it will be recorded, which kind of event was that? So this will be a trigger. And then analyzing that triggers, we can check for missing ET, like missing energy, or if that event was a displaced vertex, like I show you. In that case, we need to analyze if there was a single top, a double top, which kind of event was that, and then we can apply statistics to try to search for a new physics and beyond standard model physics. So that flux will be what we are trying to do in this analysis. So there's a lot of experiments looking for axons right now, and you can see the scale here is huge. I mean, goes from 10 to minus 15 to 10 to the 3 GeV. So there are some supernovas observations from cosmology, beam dump experiments, electron positrons, of course, gamma scattering, and also what we will be looking is this high mass region here. That's where the LHC is more sensible. So we are trying to expand this high energy, high mass area here for the axial mass. Okay. So this is, of course, because of the energy of the LHC, it's pretty high. So that's the region we are looking for. So we have one paper up to now, and it's a heavy ion paper looking for axion scattering. So here we can see some of the results that could exclude the axion mass up to 60 GeV. And this was only a few events, like you can see here, it's from the lead-lead collisions. And here, I think they say in the paper they have like 15 events or so. And then they could look for photon-photon scattering, also photon-photon to pair of electron positrons here. And then you could compare that with the theories that could predict that you have an axion in between here, the photon scattering of that model. Of course, in this case, the axion is not a stable particle, would decay again with photon or only serve as a mediator. But we can have theories when this axion would be the final state of the dark matter. And then in that case, the parameter and the search would be different. So those every time those plots it's always very dependable of the model that you are searching for. So, and then one part of the work I'm doing, it's related with machine learning because, like I said, we have like 1 exabyte of data, and then it's impossible for us just to look for that and analyze all that data using human or statistical. And I mean, it's possible, but it would take long. And to try to separate and discriminate the data, you need machine learning, you need advanced techniques in data analysis. And one of the things we are doing there in Sprace, it's actually that. So using machine learning to try to identify and discriminate between signal and background events for that. For example, one of the analyses that we are doing, and we are already in calibrating that, it's the top and top production plus Z that decays in hadrons here, both for the run 2 and run 3 data. So when we say here like center, center of mass energy of 13 TeV and 13.6 TeV, we are saying about the run 2 and the run 3. And of course, we need to process like the order of 100 terabytes of data. And for that, we train a deep neural network, and we calibrate and we run that locally, because that's one of the challenge that we had. Because usually the users from CERN, they use this environment that called LX+. That's basically a computing grid from the CERN that provides for all of its users. But the problem it is that LX Plus depends a lot of the fluxes because we are competing resources with everyone in the world, everyone using the experiment, different experiments actually. And at Sprace, we have a dedicated facility. And one of our challenges was to translate the environment of the CERN to the same environment here at Barra Funda, for example, and using also our tier 2 to do those kinds of analysis. And we proceeded to do that. I mean, we have a modest computer grid here. We called it HAL. If you know the 2001 Space Odyssey, you would get the reference. So here you can see some specs. So it's about 300 CPUs, 600 gigabytes of DDR RAM. We have only 3 GPUs. We're trying to improve that, but it's complicated. And we have like 20 terabytes of storage across all 7 machines. But the great advantage of this is because it's ours. I mean, we can use this only for the postdocs and for the students. And I mean, most of the time, we can process anything anytime we want because we have total control about this. So this is one of the main advantages. And with that scenario, we already could reduce, like, for example, one analysis that we are running from the run 2 from 2018 data, from 8 to 2 hours to like less than 5 hours in our environment. This is compared to the LX Plus environment, because people need to send the data and process this across the whole LHC wording, LHC grid. But in our environment, we could reduce that time considerably. This is just our login screen. That's the how. And one of the advantages that we have also is because we have a dedicated link to the tier 2 from LHC. So we have all the data stored at the tier 2, and then we can process these like in a computer that's basically side to side. This is just a schematic of our architecture there. So we have 7 machines, all running Ubuntu. That's another advantage because CERN, if you know, they use the Alma Linux or CentOS. It's not ideal because I believe most of users are used to Ubuntu and install stuff on Ubuntu. And I think the documentation is also easier to do in Ubuntu. That's the personal point of view. People will argue with Arch is better, but I mean, you get it. So we log it from SSH anywhere we want. So, and we have some specific tools like HCondor and Slurm to process these all together and to give all those machines to operate in together. And about the machine learning part itself, we developed a framework that's called Macaxeira. Here you can see the acronym, it's pretty huge. But basically what it does is, we take data from a, a library that we use for columnar analysis in Python. So this is the Pepper. It's a library developed by the people from DAISY in Germany that use only Python to do analysis with the data sets from CMS. If you know about a little bit about analysis, you remember that mostly of the majority of the cases people use C++ or use some code that's very, very specific and very not well documented to do the analysis. And the great advantage of Pepper is because it's new, use Python, can run parallel, and it's very well documented. So one of the reasons that we are using this, it's a collaboration from people from DAISY that we are also collaborating with them now. And then after we run Pepper, we have a data frame, or we have like a data set that extract the data from the experiment that we already went with all the cuts, all the triggers and stuff like this. And then we give this to Optuna, that Optuna will run Macaxeira. Optuna, if you know, it's it's a library that can parameterize and find the best parameters for your DNN or your machine learning model. And then we run Macaxeira, we try to get the best parameters, get the best results, do like some model evaluation, and then we have a pre-trained model that we'll use again for the Pepper to discriminate between signal and background. So it's a cycle here to get the best parameters to discriminate between signal and background. So one of the advantages of this Macaxeira framework that we are using is that it can read data from any tabular format like pandas, Parquet, CSV. This is the formats that industry are using. I mean, pandas, Parquet. This is very common. It's not root. That's the common in the case of LHC files, datasets. Also, this framework that we are using can accept different architectures like DNN, recursive neural networks, boost decision trees, and a lot of others. I mean, because we need to write, of course, and this Macaxeira is just like the operator of these different architectures in a sense. Supports parallel training, so we can train this model using CPUs, GPUs, a lot of machines at the same time, or the three of all of these together, so we can use multiple CPUs, GPUs, and a lot of machines. So this accelerates a lot the time of training because, like I said, we have a bunch of terabytes of data, and to train all of that would cost a lot of time if you do like in a regular one-threaded format like Python generally use. And also, like I said, the API parameters is using Optuna, and all training can be done also in scripts or through Jupyter Notebooks, what also facilitates to see what exactly what you are doing. So this is just a model evaluation that one of the data sets we are working. So this is a model for that try to discriminate 2B jets for that TTZ analysis that I show you guys. So this is one of the results, the Hawk curve about 92%. But of course, this is not the final version. We still need to check, especially here in this high-end region. This is our problem right now. We need to better discriminate in this region here between background and signal, because this region will give us the likelihood and all the statistics of the analysis that we are being doing. So this is a problem that we are facing now, trying to find better metrics for that. This is just a screenshot from the model running. So this is a task plus HTCondor. So you can see here all the jobs from all the data sets being given to different machines. And then we see the load of memories and all the splits of the jobs that being done and or being processing in the real time. And this is a screenshot from the the output from Optuna. So in this case, we run for 1,500 trials about, and optimizing for 7 different parameters from DNN. Here you can see the parameters, that batch size, dropout height, focal alpha, focal gamma. I would not explain these, but this is some machine learning parameters for this kind of architecture. That's the DNN. And then you can see that the model tries to find the best combination, and we try like to optimize this using a algorithm that it's already written in the code. Okay. So this is my final slide. Just the general perspective. So this praise develops research that can support machine learning and data analysis and among other activities. So the LHC, of course, is one of the biggest machines of the world. The experiment can generate a lot of data. It's generating a lot of data right now, and we need some novel facilities and novel ways to analyze that. One of the models that I've been studying, I've been studying dark matter since my master and PhD, and now we are studying this axion model that try to apply this to and to compare, to search for this in this new data that are being taken from LHC. And we hope that this axion could set some restraints through the parameter space from dark matter and from the for this new physics analysis as well. And to conduct this analysis, we are developing our own infrastructure, our local infrastructure that can process and compute data with high performance computer that we say, like HPC, using advanced techniques of machine learning and data simulation as well. Yeah, I forget, this is a new part we have been doing the last months, not in this presentation, but also in CERN, when you are working in an experiment like CMS, you can ask people to generate data in Monte Carlo for you. But usually those requests take months. Like last time, a colleague postdoc of mine, I think take like 2 months to generate one sample. But we are trying to study now how we can produce those kind of data, Monte Carlo simulations as well in our local facility. And we believe that in the next few months, we will be also could generate that, and then we'll be like independent in a sense from the grid from LHC. That's nice because we don't know if that resources will be always available for us. My supervisor thinks not. that's one of the reasons that we are doing this effort to produce everything locally. And also we can learn and we can apply these to different scenarios and different efforts and etc. And I think that's it.
Thank you so much for a wonderful talk. Questions?
So thank you for the presentation. If I understood correctly, there was a slide where you were constraining the mass of the axion as well some parameter. I think it was a Wilson coefficient of some for the axion decaying to gamma gamma, I guess.
Yes.
And then I would like to ask you if because I guess that you guys are only considering a single effective operator for this in this case. Are you guys also, is this something that the collaboration is considering to include additional effective operators to including the axion-like particles and perform a global analysis of all the possible effects that can be generated in this EFT perspective?
Yes. Actually, this is, sorry, I didn't put the reference here, but this image is not ours. I took from a paper. I should put the reference here if I upload it. But yes, we could look for different operators. And like I said, if you change the model, you change the analysis and you change the everything that subsequent, like the fixes and stuff. But yes, you could like interpret this more global way. Also doing reinterpretation of the previous data, like run 2. Right now, we are just looking for run 3, but it's possible. I mean, the possibility that we can work with run 2 data is also open. I mean, and we can also change this for a more global scenario. Usually, those kinds of analysis, they have a benchmark from a group. For example, LHC, the CERN actually, has some theory working groups that define some benchmark scenarios, and then that's what we use usually. But I mean, if we uh, note that we can use some different parameters, yeah, we will go for it. I think. I don't know if answer your question.
Yes, yes. I just would like to know if is this something that the collaboration is considering about doing, or is something planning, or.
Yeah, we have some theory groups that work on
There-
benchmarks for all the experiments, and then we can look for the same thing together. Because otherwise, I mean, as we have like some a different open parameters, I mean, free parameters, we can. If anyone look for a different thing, we would be not we cannot interpret the data. So that's one thing.
Okay, thank you. And if I may ask one quick question,
Yes.
you guys are using machine learning techniques to extract the signal,
Yes.
and even for these axion-like particle searches, right?
Yes.
And how are you training the neural network? Are you also including the new physics signal?
Yes.
And how what is the bias that the neural, is there something that we could indicate the bias of the training, or the hypothesis of the training data that you are using to train the network?
Okay. So we have like the Monte Carlo that we generate from the signal that we want. And also we get depends of course of the background that we are expecting, but we give to the machine learning, to the model, oh, this is signal, this is background, and then the whole data, and then we label the data, of course, and do the flow from the machine learning part. I mean, you separate between test and train, and then you after you have a training model, you apply this to the real data. But we train mostly on Monte Carlo. But of course, we calibrate these with with data afterwards.
And this Monte Carlo data contains the standard model predictions plus the new physics signal, like the
Yes.
action.
Yes, both.
And is there if you turn off the new physics signal, the performance of the neural network for detecting the signal events, does it change? How robust is the training
Change,
against
but you need
the?
to, I mean, for the machine learning part, for the model, you need to state clearly what you want to be trained for. I mean, if you are trained for a signal that's not, I mean, you could train for a signal that's not new physics. That's why we do actually in the TTZ. TTZ is not new physics. It's just we are just looking for a measure of cross section, a specific cross section. And in this case, the Monte Carlo that we have is standard model, and we pass that to the DNN and then train in that data set, and then we apply that to the data, to the real data.
Okay.
Hi, thanks for the talk. I have a few questions about your work on the. Can you go to the top quark thing?
Oh,
Yeah.
the
The
diagrams?
yes yeah, that one. You didn't really tell us much about it, but I'd like to ask you some questions. First of all, why do you say it is dark matter?
It's not. It could be.
No,
It's
no,
a
no.
model.
But you cannot. I mean, if you say it's dark matter, you have to show it. It can't be
Yeah,
dark
yeah.
matter.
No, we still. I mean, this is one thing I didn't
I mean,
say.
it's fine to say it could be, but
Yes.
if you say it is,
Yes.
then you have to show.
Yeah. Yes. I mean, we didn't run the whole. I mean, the whole parameterization of dark matter of this kind of model yet. I have the paper. This is based on a paper, not mine. But yes, we are planning to identify this with the actual cosmological dark matter. I mean, it's not. I know what you're saying because my PhD was in actually dark matter, and then these I'm not showing here, but we have a lot of parameters to try to estimate these as actual dark matter or not. But
Yeah, because I mean, it's not so easy to
it's not so easy. Yes.
yeah.
No, it's
Okay.
just to illustrate. I mean, I'm not entering details here, but we have these
Okay.
well
Then I have a
written
second.
somewhere.
Then I have a second question
Yes.
related to the channel that you're using. Why is it interesting to use this channel?
The double top?
Yeah.
Because the cross sections is huge.
Okay.
Yeah, we have like
but
this
but
production is one
exactly
of
because the
the
cross section is huge,
yes.
maybe it's not so easy to see this, right?
Yeah, but yes, one of the reasons of the top punch top, it's just because the cross section is one of the main productions that we have. Also, the single top is not that much, but yes, we want to study this because if this thing would happen like we have sensibility enough, even though if the cross section is low and the possibility is low, as we have a lot of events of this kind, it would be easier to find this in the.
Yeah, that's
in the
what
data.
is not very clear to me because exactly you have a lot of background for
Yes,
this,
of course,
right?
we need to estimate the
Yeah.
background.
So I was just curious why you choose this.
Yes.
Because I would think it would be easier to look in some resonant kind of a channel
Yes.
or bosons, with, related to boson, Higgs,
Yes.
right? So I was really curious why you would choose this channel.
Yes.
So it's just because the cross section is huge, but then I can say the background is huge.
Yes, as well. Yeah, but as we are working with these techniques of discrimination in signal and background, even though if we have like a huge background, we believe, of course, I mean it's not state in stone, but we believe that we can discriminate at least to give some limits on that. But of course, for example, in my PhD, I work with the resonance scenario, so it's easier to see in the data, of course. But also our group has experience on this on the water production. So for us, the analysis flow, it's already, we have the knowledge of how to do this.
So I have questions. Is it TT bar Z process? Are you trying to connect?
No, not yet. I mean, that
So
is
what
just
are you trying
a
to
measure
see
of,
there?
yes, that's just a measure of cross-section. I mean, it's a very difficult cross-sections to measure. This is the work of a colleague of mine from her PhD that's now also a postdoc. But she used some machine learning to try to estimate that. And we are taking on that and then following for this new scenario and also adapting, because she did for run two, and we are also doing now for run three. But yes, we're not sure if you can apply new physics to that scenario because the cross section is very restricted, and there's already some works that show from this kind of TTZ what we can find or not. And what we are actually doing is try to find this hadronic decays. It's not like any kind of. This also limitates the final states. But I mean, it's a open.
Yeah, I think there are some few works from self because I also have a work theoretical easy process,
Oh yeah.
but it was in leptonic.
Yeah.
As
Yes.
Renata was saying, hadronic is
Yes.
full of.
Yes.
So
That's a
you
problem.
said that these events you just had two B jets, but you also have a lot of jets.
Yes, we have one BJet and two BJets models. I show you only the two BJets, but we have one BJets with
Are you
a
simulating
slight
the
less.
Are you simulating the background on your machine or you're collecting from
For this TTZ, we already had the Monte Carlo generated, but for example, now we need for the run 3 Monte Carlo, and that's why I say that it's taking too long to simulate, because I mean, you have a queue of a lot of people asking for simulations, and then we are studying how to produce them locally
this?
at home.
In the hadronic mode, you have till 8 jets plus extra.
Yes.
So 8 QCD jets, the QCD 8 jets.
Yeah, but I think I don't know exactly now the details, but I think we only for like we have a cut on that. I mean, it's not like we not look for everything. We're just looking
Yes,
because
but I
we
know
we
it's
lose
very hard.
systematic, but yeah, we gain in the other side. But yes.
There's no more questions. Let's thank Marcio again for his wonderful talk. So we go for lunch and we'll begin at 2 afternoon.
Jovem.
I think we can start. So welcome to the afternoon session. So before we start, we have a little announcement that about the venue. Tomorrow we'll have our in the morning session only. We will have talk at this auditorium Adma Jaffe, just right side near the park. But afternoon we'll start here. Just a moment. Now, Matthews from our UPSP group will be talking on Delian and electric precision observable analysis in the universal estimate.
Okay, so good afternoon, everyone. Thank you all for coming. Special thanks to the organizers for putting together this nice end of the year workshop for us. And yes, today I'll be talking about Drawyan electric precision observable analysis in the universal SMAFT. So basically the idea of the project is to assess the impact of dimension 8 operators in these two data sets. And this is the project that I work in collaboration with my advisor, Oscar Eboli, and also our collaborators, Tyler J, Professor Concha Gonzalez Garcia, and Peter Reimetz, who was a former postdoc here in the Institute. And I have to apologize to my friends because today I won't be talking about the game, although it's happening at the same time. But I'll promise that I'll keep my presentation short. So let me start with a few motivations. So after the discovery of the Higgs, we know that we haven't found resonance signals at the LHC. And because of this absence, we can assume that there is a mass gap between the electric scale and the scale of new physics. And because of this scale separation, we can work with the framework of effective field theories to analyze the available data we collected so far. And here in my presentation, I will be working with the standard model effective field theory, where we are basically adding to the standard model Lagrangian higher dimension operators, and those are constructed out of the standard model fields, and they also must respect the standard model gauge symmetries. And here in my presentation, I will consider only operators that are C and P even, and they also must preserve lepton and baryon number. So the class of operators that will be important for us, it starts at dimension 6 and also at dimension 8. And the idea of this math expansion is that we are basically the leading beyond standard model effects are captured by the lowest order dimension operators, where basically we are expanding the new physics effects in powers of 1 over lambda, where lambda represents some new physics scale that we don't have access yet. Okay? So basically, as I mentioned, since we want the leading beyond standard model effects, in principle we should add the dimension 6 contributions on top of the standard model ones. And since we want to compare our theory predictions with what we observe experimentally, we have to square this amplitude. So if you want to keep this 1 over lambda expansion also at the cross-section level, in principle, we would only keep the interference between the standard model amplitude with the dimension 6 amplitude that goes with 1 over lambda square. But there might be some cases where the dimension 6 square contributions can be important, and I'll mention some of those cases later on. And we also would like to include those terms in our analysis. The problem is that those terms are in principle of the same order as other terms that we are neglecting. So for example, we could have an amplitude with 2 insertions of dimension 6 operators interfering with the standard model also yields a term of the same order. And we could also have an amplitude coming from a dimension 8 operator interfering with the standard model also yields a term of the same order as the dimension 6 square contributions. So if we are performing the analysis including only the dimension 6 square terms, we would like to know how robust the results of our fit are against the inclusion of these higher dimensional terms that we are neglecting, okay? And the problem is that to access the impact of these higher dimensional operators, we have to go beyond dimension 6, so we have to consider a class of dimension 8 operators, and it becomes challenging because the number of effective operators increases once we go to higher dimensions. So if you want to include also the impact of those dimension 8 operators in our analysis, we have to make some model assumptions. And the one that we'll be making here is the one of universal theories. And what do I mean by universal theories? It's basically the case where the new heavy degrees of freedom are basically coupling with the standard model bosons, or if they are coupling with the fermions, they must couple via the standard model currents. In this way, if we integrate out these heavy degrees of freedom, we can basically write down an EFT that is only written in terms of bosonic operators after employing field redefinitions, okay? And when we make this assumption of universal theories, the number of effective operators that we have to consider at dimension 6, and now also at dimension 8, is significantly smaller than the general case. Still, it's a large number of effective operators, but as we'll see, the number of effective operators that we have to consider in the dry-ion and electric precision analysis is much smaller than that. And now, thanks to also my collaborators, including my advisor, Oscar Eboli, we have a basis for dimension 8 effective operators, and we can perform this study beyond dimension 6 for universal theories. Okay, so now let's focus on the data sets that we have to analyze, so both dry-ion and electric precision observables. So if we have an EFT that is written only in terms of bosonic operators that are characterizing some universal new physics effect, when we think about dry-ion processes and electric precision observables, we only have to consider those effective operators that are modifying the gauge boson propagators, okay? And here we can employ field redefinitions to move the effect of these bosonic operators into fermionic ones, and we can do this because the S matrix elements are invariant under these field redefinitions, so it doesn't change the physics. And when we perform these field redefinitions or equations of motion at dimension 6, we can have far fermion operators that affect dry-ion production, and also modifications to the gauge boson couplings to fermions that are also important for the electric precision observable analysis. This is all to say that LHC data and also electric precision observables, they can be complementary to each other. And from now on, I'll basically talk about the universal EFT that is written mainly in terms of fermionic operators. And the reason for this is a technical one, because most part of the tools that we have available to perform simulations, they are thought about to deal with this kind of effective operators, not corrections to gauge boson propagators. So it's just a technicality, but it doesn't change the physics behind it, okay? So why can dry-ion data be also competitive with electric precision observables? And I'd like to show this simple example. So if you consider the effect of those far fermion operators, they induce corrections to the center mass energy that grows with the induced effects that grows with the center mass energy of the process. And this energy growth can be appreciated at the tails of the cinematic distributions. And there, since the standard model prediction is very small, we can have a large signal over background ratio. And this is what you call energy enhancement effects at the high PT tails. And these energy enhancement effects allows us to derive limits from dry-ion data that can be competitive with electric precision observables, okay? And this was shown before in this famous paper, Energy Helps Accuracy by Farin and collaborators. So basically here they are considering two effective operators that are modifying the gauge boson propagators. And once we employ the field redefinitions, we can translate their effect into mainly far fermion operators plus additional effective operators that are not important for the dry-ion analysis. And here, W and Y, we call them oblique parameters, but think of them as the Wilson coefficients of these bosonic operators. And here we have the limits in purple from neutral current dry-ion channels, and in green from charged current dry-ion channels that can only constrain the oblique parameter W. And we see that the combination of the both neutral and charged current dry-ion channel are actually far better than the results from lab. And here they extract these limits, including the linear dimension 6 and the dimension 6 squared terms that I mentioned. And we would like to know if the same conclusion will hold when we start including these linear dimension 8 terms that we neglected, okay? So why the dimension 8 operators can be important? It's useful to see this table where you have the possible fermionic operators that can affect dry ion production and how their contribution scale with the energy at the amplitude level. And we see that at dimension 6, the highest energy scaling is coming from the far Fermi operators. And if you go to dimension 8, the highest energy scaling is coming from the far Fermi operators with additional derivatives. This means that if we are plugging operators from these two classes in our expressions for the cross sections, the linear dimension 8 piece will have the same energy scaling as the dimension 6 squared term. So this means that these linear dimension 8 contributions can alter the limits that we have on the dimension 6 Wilson coefficients. And now, thanks again to the basis that we have for bosonic operators beyond dimension 6 for universal theories, we can perform this study systematically on dry ion production for universal theories. And what are the effects that can appear at dimension 6 is basically summarized in this table. So first, we have these far Fermi operators that are important for the dry ion analysis, and they are the ones that are related to the oblique parameters W and Y. And then we also have effective operators that affect the observables, the processes that are defined input parameters that here we are taking to be the electromagnetic constant, GF, and the Z mass. So, for example, this far Fermi operator that is related to the oblique parameter W also introduces a correction to the muon decay, so it enters in the definition of GF. We have an effective operator that induces a mixing between the Stern-Motor gauge boson, so it affects the definition of the electric charge and also the Z mass. And we have one effective operator that is altering the Z mass, so it also enters in this computation. And once we take everything into account, we have corrections on the Z coupling to fermions, also W coupling to fermions, and the W mass. So basically, this delta G1 is just a rescaling of the Stern-Motor Z couplings, and delta G2 is basically a QED-like coupling for the Z bosons to fermions. Delta GW is just a rescaling of the W couplings, and of course, delta MW is just a rescaling of the W mass. And these shifts are basically written down as functions of the Wilson coefficients of the effective operators that I mentioned before. And we also include in our computations dimension 6 square contributions, but I'm not showing these expressions here because they are not very illuminating. And now, if we go to dimension 8, this is the list of effective operators that we have to consider for both electroweak precision observables and dry ion analysis. I'll not go through them all. I'll just highlight the most important effects that can appear. So if we go to dimension 8, first we have this bosonic operator that generates the oblique parameter U. So its main effect is to shift the W couplings without touching the Z couplings. So this parameter will be important for the electroweak precision observable analysis. And then we can have the far Fermi operators with additional derivatives that I mentioned before. And these are the ones that will be important for the dry ion analysis. We also have a far Fermi operator that is not a rescaling of the dimension 6 ones because we could construct dimension 8 operators out of the dimension 6 ones just by adding Higgs-Dagger-Higgs. It's just a rescaling of the same effect that we have at dimension 6, but this is not the case. It's a contraction that we cannot have at dimension 6. It's only allowed once we go to dimension 8. And then we also have effective operators that are modifying the Z and W coupling to fermions that depend on the momentum that is incoming to the vertex. And for the dry ion and electroweak precision observable analysis, we can basically decompose their effect into a far fermion contribution plus a finite correction to the Z-W coupling to fermions. And turns out that the Wilson coefficients of these two effective operators are not independent. We have a universality constraint that relates their Wilson coefficients with the ones from the far Fermi operators with additional derivatives. So basically, this is the summary of universal new physics effects that can appear at dimension 6 and at dimension 8. So just to remember, this delta 4F is the one that is related to the far Fermi operator that affects the electroweak precision observables and also will be important for dry ion production. At dimension 8, we have this Wilson coefficient that is the coefficient of the bosonic operator responsible to generate the oblique parameter U that is basically inducing a correction to the W couplings without touching the Z couplings. And then we have these 4 Fermi operators with additional derivatives that will have the same energy scaling as the dimension 6 square contributions coming from the dimension 6 4 Fermi operators. And basically, in our analysis, we have a total number of parameters equals 8, 4 parameterizing the effects that can be generated at dimension 6, and other 4 parameterizing the effects that can be generated only at dimension 8, and the effects of all the other coefficients that I haven't mentioned before. They can basically be encapsulated into a rescaling of the coefficients that I did mention. So when we look to the universal new physics effects in the Drawyer electric precision observable analysis, all the new physics effects can be encapsulated in these 8 Wilson coefficients. Okay, so now this is basically the data sets that we consider. We have the traditional Z and W pole observables, and also we have the neutral and charge current Drawyer channels from the run 1 and run 2. And this is the first set of results. That is a comparison between electric precision observable analysis and Drawyer data at dimension 6. So including only the linear dimension 6 contributions. So the electric precision observable analysis can only constrain 4 combinations of coefficients. And at dimension 6, you only generate 3 of them that are parameterized by these parameters here. And the limits from electric precision observable analysis are in blue on these pair of parameters. And the important point here is to notice that once we add Drawyer data together with electric precision observables, so which are shown in this red region here, we see that the limits on delta 4F, which is this Wilson coefficient, that is the Wilson coefficient of the 4 Fermi operator, improves by more than an order of magnitude. And this is nothing but the energy helps accuracy effect that Farin and collaborators point out before at dimension 6. So this is expected, okay? So now let's go to dimension 8. And as I mentioned before, once we go to dimension 8, we have one additional effective Wilson coefficient that is related to this parameter U. So in the electric precision observable analysis, we have 4 coefficients instead of 3. And because of these additional coefficients, we have cancellations in the Z couplings as well as the W mass along this direction. And the only observable that can constrain a direction that is orthogonal to this one is the W width. But the W width is less precise than the Z pole observables. So this means that we have, once we go to dimension 8 analysis of electric precision observables, we have strong correlations in the parameter space that are being caused by when we include this dimension 8 Wilson coefficient that we did not have before. So the situation, the limits, when we go to dimension 6, they are worse than the dimension 6 analysis. And now if we include Drawyer data, so basically this second column is the same one as the first, this second column is the same regions as in the first one, but we are zooming in the region that is constrained by the combination of electric precision observables and Drawyer data, which is shown in red. And we see again that once we include Drawyer data, the limits on this coefficient delta 4F becomes much better than before. So Drawyer data, once we go to dimension 8, helps to break this strong degeneracy that we have in the electric precision observable analysis. And not only that, also, since we are breaking this strong degeneracy, the limits on the other Wilson coefficients, for example, C51 and C3W2H4, also become better by more than a factor of 20. So when we go to dimension 8, the combination of Drawyer data and electric precision observable becomes even more important because Drawyer data is able to break these strong degeneracies that we have in the dimension 8 analysis of electric precision observables. Okay, so this is the first conclusion that is important. And then I would like to show you what are the effects on these 2 oblique parameters W and Y that I mentioned in the beginning. That are the same parameters that were constrained by Farin and collaborators considering linear dimension 6 and dimension 6 square contributions. So for the 4 Fermi operators, just to remember these oblique parameters are related to the 4 Fermi operators, and when we go to dimension 8, we have these additional 4 Fermi operators with derivatives, okay? Now, this is the analysis considering only the dimension 6 operator, the solid region, basically represents the limits including the linear dimension 6 and dimension 6 square terms. And the dashed line includes only the linear dimension 6 contribution, and we see that the results, they don't change much. So basically, this means that the analysis, the results are robust against the inclusion of dimension 6 square contributions. Now we go to dimension 8, and pay attention to the range of the y-axis. I had to change it once we go to dimension 8. So basically, if we go to dimension 8, so now we are including the linear dimension 8 contributions from the four frame operators that we had, that we didn't include in the dimension 6 analysis. First, we see that the limits on delta 4F, so which is basically the oblique parameter W, becomes worse than the dimension 6 analysis. It's quite restrictive. The limits are quite strong, but it's slightly worse than the dimension 6 case. And we can understand this by looking at the correlation it has with the four frame operator with additional derivatives that we have when you go to dimension 8. And this four frame operator is basically constructed out of the same currents as the dimension 6 ones. The only difference is that we have derivatives. So it's expected that they have a correlation. So that's the source of this increase on the confidence interval for this effective operator. Okay, and now to understand what happens to this parameter, which is this Wilson coefficient that is related to the oblique parameter y, we can trace this behavior to the correlations it has with the four frame operators that are generated at dimension 8 that only affect neutral current drawing processes. So for example, this is a four frame operator that contains derivatives and also constructed out of the same currents as the dimension 6 one. And this is the four frame operator that is not a rescaling of the dimension 6 ones. And we see that we have these strong correlations, especially this one is this non-elliptic correlation for these pair of coefficients. And these correlations are the source of the increase of these confidence intervals. And we can understand these correlations by looking at this cross-section ratio plot. So basically, here we are plotting the EFT cross-section normalized by the standard model one as a function of the center mass energy of the process. So whenever these lines are far away from one, it means a large deviation from the standard model prediction. So if we include, and here we are including only these three effective operators, okay? So first, if we include the linear dimension 6 contributions only, as we increase the center mass energy of the process, we see that we have a deviation from the standard model prediction as expected as we increase the center mass energy of the process. Now, if we include the linear dimension 8 contributions without including the dimension 6 square contributions, we have a cancellation between the linear dimension 6 piece and linear dimension 8 piece that is coming from the four frame operator that is not a rescaling of any of the dimension 6 ones, and because they have the same energy scaling, these two terms. So the cross-section is basically dominated by the linear term coming from the four frame operator with additional derivatives. Now, once we include the dimension 6 square contributions, we have a cancellation between the dimension 6 square contribution and this linear dimension 8 contribution coming from the four frame operator with additional derivatives. And because of these cancellations here, we have an increase of the confidence interval of this dimension 6 Wilson coefficient. So basically, this is all that I want to say because these are the main findings that we had in our work. So basically, we performed this analysis of Drawing electrode precision data going beyond dimension 6 in universal theories. We saw that drawing data, the combination of drawing data and electric precision observable becomes even more important as we go to dimension 8, because drawing data is able to break these strong correlations that we have in the dimension 8 analysis. And also, once we go to dimension 8, the limits on this Wilson coefficient that is related to the oblique parameter y becomes worse than the dimension 6 analysis because of the correlations it has with the additional dimension 8 four frame operators that only affect neutral current or drawing channels. That's all that I want to say, so thank you.
Thank you, Matthews, for the wonderful talk. Yeah, now we have some questions.
Thank you, Mateus. So I have two sort of related questions. One is more of a language question. So when I think of electroweak precision observables, universal, as you said, or oblique. I think of S, T, U, and then X, Y, and W. You
Yes.
showed. So you showed us that there is the W and the Y appear in your Drellian parametrization, and the U also appears, as dimension 8, which we know from the other parametrization. The first question is, what happens with S and T? You have
S and T, they appear actually. So
so I didn't see you
no,
mention them
yes,
because it's like that's what I mean by language. So
I
didn't see
avoid
the-
adding these. So you were right. Let me see if I have the backup slides here. So yeah, so basically these are the oblique parameters that are generated
this one, yeah.
at dimension. So these 4 are generated at dimension 6: S, T, W, and Y.
Right.
Okay, so Y cannot be constrained by electric precision observables because because their effect on the electric precision observables can be thought as a rescaling of the oblique parameters S and T.
Right.
So basically just they can be the effect of the oblique parameter Y can be absorbed in combinations of the oblique parameters S and T. So these are the 4 that are generated at dimension 8, and maybe it's more interesting if I show you something before. So basically, okay, so these are the traditional oblique parameters that we have. They're normally thought as the expansion of the gauge boson self-energies up to this order in the momentum expansion. And now to include the effects that are generated at dimension 8, we have to go 1 order above. So we have to add these additional oblique parameters that we define as the prime parameters to include these contributions that can be generated at dimension 8. Actually, not all of these guys are generated at dimension 8. The only ones that are generated are these ones. So the oblique.
This is what I really wanted, to know which ones appear at dimension 8.
Yes.
So and which, because S and T appear at dimension 6, and then typically then that means you didn't emphasize them because Drellian doesn't affect that much their the determination.
Yeah, so basically S and T, they because it's we see that they are we have the limits directly on the oblique parameters, but I avoid to say that the limits that we have on these Wilson coefficients are directly translated into oblique parameters because we have to make this rotation.
Right.
But the idea is that basically the oblique parameter S can be thought of as this CBW, and T can be thought of this C phi 1. So basically, those coefficients are mainly constrained by electric precision observables at dimension 6, and the impact of them in Drellian data is very small. Now, if we go to dimension 8, Drellian ends up being important because here. So if you see C phi 1, it becomes highly correlated with this Wilson coefficient that is related to the oblique parameter U at dimension 8 in the electric precision observables analysis. And CBW not that much, and what else? Well, delta for F, but C phi 1, it's correlated with this coefficient. So once we add the combination of Drellian together with electric precision observables, because we are breaking these correlations between delta for F and this dimension 8 Wilson coefficient, the limits on C phi 1 also improve. We were a bit surprised when we saw that. But this is nothing but the fact that we have these strong correlations in the dimension 8 analysis. So if we keep at dimension 6, the limits on S and T are mainly coming from electric precision observables as expected. But if we go to dimension 8, the limits on the oblique parameter T, that we can think about as C phi 1, becomes better because we are breaking this correlation that it has with the oblique parameter U.
Now, the related question is, suppose people are talking about, post-LHC machines and E plus, E minus, etc. So in principle, there will be a similar analysis and E plus, E minus for Fermi. You have Drellian. Have you guys thought of what would be the impact of doing similar analysis? Of course, the operators are different. But there will be something to be said, right? I mean, people are redoing
Yes.
a lot of the analysis for the dimension 6 operators for these machines. But have you thought of, prospecting these kinds of things?
So not yet, but I think this is the part that is more challenging because we have to go beyond tree level. Because we have enough precision at the future machines that we have to consider effective operators that are also loop generated. So it becomes, we could extend this by assuming more statistics and just improving the limits at the tree level Wilson coefficients. But that I think is, we have to be careful because we also have enough sensitivity to test the effects that are generated at a loop level. So we have to go beyond tree. So it uh-huh. At tree level, this is only at tree level, and then we have to convince.
Well, thanks for the presentation. I noticed that you use MatGraph,
Yes.
right? And Peach and Doves. How many events did you generate for that?
Oof. I don't remember, but normally what we try to do in this more technical part, we have these distributions that are, because these Drawing distributions are, we can safely impose cuts at the generation level to separate the simulation into disjoint parts of the phase space. Mm-hmm. So normally what we do is just to break down the simulations in small pieces of the phase space. So normally we use, I don't know, 50,000 events or 20,000 events. I don't remember by heart.
Okay.
But whenever, so let me say that whenever we are doing this, we make sure that we have enough statistics to rely on the Monte Carlo predictions.
Okay. And that final results that you show, it's valid for any lepton for the final state?
No, actually, these, so we have a few, so most part of the data that we have, they are recast of direct searches. So they are searching for new heavy Z prime or W prime gauge bosons, either in the electron or muon channels. So we have to go to the also full detector simulation, and there's a difference between electrons and muons. So I think the only distribution that we have that is valid for both electrons and muons is from the run 1 data from Atlas, because they unfolded the data. So they removed the detector effects.
Okay. If we don't have any more questions, let's thanks Matthews again. After this talk, we'll have a coffee break, and we will have the last session of the talk. And then we'll have welcome drinks inside. So now, Joao Vitor from IFUSP will be talking on the measuring the expansion of the universe through gravitation.
Hello. So first of all, thank you for the organizers. So hi everyone, I'm João. I'm from the cosmology group here at the Institute. Today I'll be talking about things not related to particle physics at all, so I'm sorry. But I'll hope you like it. I tried to make it as simple as possible. And yeah, so today I'll be talking about gravitational waves in the context of trying to measure the expansion of the universe. So I'll give a brief overview about gravitational waves. What is it that we call dark sirens, and how what are the usual ways that we measure the expansion of the universe with these things. Then I will talk about a new method that I have been developing here at the Institute to measure the expansion of the universe with these things. And then I'll give you some real measurements that we recently did. So just to start, I don't think I need to tell you that we have entered the era of gravitational waves. These are a very hot topic today, and gravitational waves can imprint themselves on many observables in the universe. And today I'll be talking about mainly the things that we observe today, which are these high frequency gravitational waves, which are caused by the merger of compact objects, such as black holes or neutron stars. So what do the detectors actually observe? They observe something called the strain signal, which is basically a combination of two components of the gravitational wave. So it's an H plus polarization and an H cross polarization plus some functions here that depend on the sensitivity that you have on your detector. So that's the landscape of the thing. You have a binary system here merging, and then they produce these very fast gravitational waves, and then they eventually merge to a single object, generate a black hole. And this is what we detect with LIGO, for example. So if you go to general relativity, you obtain a rather simple expression for these H plus and H cross polarizations, and they depend on some astrophysical properties, mainly the chirp mass, which is basically a combination of both of the primary masses of this binary. From the cosmological point of view, the exciting thing about these waves is that they are inversely proportional to the distance that they are from us. So this is very interesting. However, there's a current problem. The problem is that the distance has a degeneracy with the inclination of this binary system to us. So as this signal is very fast, we cannot completely disentangle these two things. And for now, the constraints that we have on the distance of these objects is very poor. So I wanted to show you guys the first three catalogs that we have with LIGO today. So how do you read these? So you have basically two primary objects that merge into a final object, which is in the center of these events. What I want to highlight is that the vast majority of these events are the merger of two black holes. So it's a binary black hole system. These systems we call dark sirens. Why dark sirens? Because we detect the gravitational wave, but they don't emit light. So we don't know exactly which galaxy they are coming from. From the galaxy, we would also be able to estimate their redshift. In fact, there's only one event in which we detected the light from the event, which is this JW170817, which was the merger of two neutron stars, which created the kilonova. So this is the only event that we call bright siren so far. So the takeaway is that the majority of these events are dark sirens. We don't see them, we just hear them. And we would much like have the two ingredients, the luminosity distance and the redshift, to constrain what you call the Hubble diagram, which is basically this dl and z relationship. And from this relationship, we could constrain things like the Hubble constant, which is the rate of expansion of the universe today, and other things such as the density of matter today. Now, as we usually don't have these two ingredients, we cannot do this direct inference. Of course, we don't want to stop here. We want to use these 99% of the events we detect to say something about the expansion of the universe. So we must add this information, this redshift information in some way. I'm going to show you how we deal, the usual way that we deal with these dark sirens so far. So this is the picture. Suppose that you have an event in the sky of a gravitational wave, the error bar, the area that you think that event is huge. So this is the area in the sky that you think the gravitational wave is coming from. And then by chance, suppose that you have a galaxy catalog in the same area of that event. Now what do? You basically account for all the galaxies inside that area, and then you assign a probability for each of these galaxies of being the host to that event. This is what we call a line of sight method. We take all of the galaxies along the line of sight, and we assign a probability. So this probability will depend on many things, and majorly by of the luminosity. So the higher luminosity, the higher the mass, and then probably the binary black hole came from that very massive galaxy. So that's the main idea. So each galaxy will have a different redshift, and each different redshift will give you a different H0. So that's basically it. That's what people from LIGO usually do. And the posterior for H0 is this red thing right here. It's terrible. Why? Well, first of all, the galaxy catalogs are incomplete. It's not true that the galaxy catalog that you have will have the host for that event. So you have to account for that. Second of all, the error bars on the error are huge. So you account for thousands of galaxies in this type of analysis. So each galaxy will have a very different redshift from each other, and then you wash out this posterior. So these are the main problems that we have to deal with today. So what people from LIGO usually do is they add the posterior from the only bright siren that we have, and then we have this better thing, which is still not enough to tell us something about Hubble tension. I don't know if you know, there's a crisis in cosmology called the Hubble tension, which is basically the difference between measurements from CMB, which is this pink line right here, and the local universe from experiments like SHOES, which measure the expansion of the universe through a method called the distance ladder. So there's this 4 sigma tension, and we don't know why. We would much like to get the answer through gravitational waves. But so far, the error bars are huge. Okay? Now, I wanted to show you the prospects for this business. So these are the current facilities that we have with LIGO. We have 4-kilometer arm lengths for the detectors. And in the future, so in 2 years, we will have the final run of LIGO, the run 05, the 5th run. We will detect around some 300 objects. We already have some 200 objects with the 4th run, which is already public. But then we will have something around, we expect something around 300 with the 5th run. Now for the future, for the next decade, we will have, I think so, 2 detectors, one in the Europe, which is called the Einstein telescope. It should be like a Dorito-shaped thing, 3 co-localized detectors. It may not be like that, it may just be like 2, still being discussed, I think. And then we have also Cosmic Explorer, which will be a huge detector in the United States, which will enhance both the sensitivity to these objects and the number of objects. And we have tens of thousands of objects, and we will go much, much deeper. So for now, LVK goes only to redshift 0.5, and Einstein telescope and Cosmic Explorer will go to Z30. So this is very exciting news. So with that many objects in the future, how can we deal with them in a way that's not individually? So the way LIGO does these things for now is in an individual way. So they go individually for each of these events, and they obtain a posterior on H0, and then they combine everything to a final posterior, which is what you're seeing here. Can we do this in a better way? This is what we're trying to answer in a work we did last year with these people right here, in which we say, yes, we can do this in a much faster way by looking at all of the events together. How? By taking advantage of the 3D distribution in in a method that we call peak sirens. So what's the idea? The idea is that, okay, galaxies have the redshift information, but they don't have luminosity distance, right? On the other hand, dark sirens have the luminosity distance, but we don't know their redshift. We don't know exactly which galaxy they came from. But the thing is that both of these things are tracing the same thing in the universe, which is the total matter in the universe, right? So where there are more galaxies, you should expect that there are more binary black holes or something. So if you do a cross correlation between these two things in space, it won't be zero. How do you do this cross correlation? Well, it's pretty simple. You subdivide your galaxy map into slices of redshift, and you do the same for your binary black hole map. You subdivide it into now luminosity distance shells, and then you make this cross correlation between different shells. What happens when we do this is something very funny. When you do this cross correlation, you have a 2D matrix which traces exactly the Hubble diagram, which is what should happen. These are two rulers to a same distance. So when you compute the cross correlation, you have that there's a peak on the cross correlation when a shell in luminosity distance corresponds to a shell in redshift. And this already tells you the Hubble diagram. So this is a very direct way of seeing the Hubble constant. The slope that you're seeing here is basically the Hubble constant. So the nice thing that we've shown is that the position of these peaks don't depend anything about the power spectrum or the things that you're computing underneath it. It only depends on this relation right here. So the data is there. You don't need to assume anything, any model. You just go there, subdivide your maps, compute the cross correlation, and you see this Hubble diagram. And from that, you can already infer something about the Hubble constant. Okay, how did we do this? Well, we basically, I won't get much into detail, but the thing is that we can simulate galaxies, and then given a configuration of detectors, we also simulate dark sirens on top of these galaxy simulations. Then we can simulate as many as we want, and then taking the average, we have a theoretical expectation value for this cross correlation between different shells I and J. And also from that, you get the covariance between these different slices. So now you can go and you can, I won't get much into detail, but you can simulate at any given universe. So in this case, for a different H0, you can basically make a different simulation, and then you get a different slope. So knowing this theoretical expectation value and the covariance, you go there, you measure something, and with this, you can make some inference of the H0, for example. So these are some forecasts. So for the final run of LVK05, which will start in about 2 years, we expect that with this peak sirens method, we can constrain the H0 with around 4% precision, which is already much better than what we have today with 03 and 04. But the interesting thing is when we go to future probes, because then we can actually get sub% accuracy with this method. And this will certainly tell us something about Hubble tension. So we can even probe different models for dark energy, for example, W0 WA, which is something very hot today because DESI measured a different value from a cosmological constant. So we can also probe this with peak sirens in the future. Now, this is very nice. Can we see the peak on future data is another question. After all, we already have real data, right? We have LVK04 already public. So this is a question that we are answering just now. We are submitting to archive in this week, I guess, right? Oh, nice. So go tomorrow on archive. So yeah, we try to answer this question. So to answer this question, we are going to use LVKO3, which was the data that we have at the time, and also because the galaxy catalogs that LIGO uses only accommodate the events from LVKO3. Now, the thing about LVKO3 is that the data is very poor localized, both in distance and the area, as I've shown you. So to see the peak, we only use 2 points. The only bright siren that we have, but we didn't use a ratchet, only the distance estimate, and the best localized dark siren that we have, which has a 18 square degree error. And then we use this Glade Plus real galaxy catalog to make this cross correlation. And what happens when you do this cross correlation? Ta-da! This is the peak on the cross correlation. Of course, it's not beautiful as the 2D matrix I have shown before. It's not continuous. We only have 2 events. And then here's what you see. What you see is the bright siren, and here's the dark siren. But yeah, we see the peak in the cross correlation as we expected. And then we have the data. We have some simulations. So we replicated some simulations of the Glade galaxy catalog and replications of these bright siren and dark siren. And then with this, we could make some inference. Not only that, we didn't just make an inference on H0, we can also make an inference on the bias of these parameters. For those who don't know, well, what we actually compute from the theory is the overdensity of the dark matter mass, which is this delta M. What we observe is our matter tracers. It can be either galaxies, it can be either these gravitational wave sources, and we make a very simple assumption that at large scales, these 2 things, the overdensity of X and the overdensity of dark matter, are related through a linear bias. So we know for the Glade Plus catalog of galaxies that the bias is roughly 1, but we don't know what is the bias of the gravitational waves. So we let them free, and then at the end, we do the inference for both of these parameters. So these are the results for now that we have. So if we only include the dark siren, things are not very great. But if you include the information from the bright siren, then we have a constraint on H0, which is very competitive to what LIGO has with their current 4th catalog, with the way that they constrain H0 with the line of sight method. So this is very interesting, and we can also put a upper bound on the bias coming from these objects. So another interesting exercise that we did is that the signal to noise ratio goes with the square root of the number of gravitational wave events. So we saw that if you multiply the events like this dark siren that we have by 100, we can actually have which is something that it's possible with LVKO5, by the way. We can get a precision of 4%, just as we predicted in the previous paper. So this is pretty exciting. So yeah, just to conclude, so I've shown that cross-correlating gravitational sources in galaxies already provides you a cosmic ruler, so a relationship between luminosity distance and redshift, and we have shown that we can do this in a model-independent way. So the current data already shows the peak, as I showed you. So we have these constraints. I have shown you that the 2nd generation, which is the current, can achieve a 4% precision on H0. And in the future, with the 3rd generation, we can actually get a sub% precision. And then there are many things that we want to explore regarding the peak sirens method. So the first of all is to use LVKO4, which is already public. But for that, we need to build another galaxy catalog because LVKO4 events are much deeper. in Redshift, so the Glade plus catalog is very shallow. They don't accommodate these events. So for now, my job for now is to build this Galaxy catalog. And then there are many other things that we want to investigate. This is more technical. So yeah, that's it. Thank you.
Thank you, Joe, for this wonderful presentation.
Thank you, João, for a very nice talk. I have a couple of questions. First of all, remind me of the numbers for each node for the other two measurements. I mean, the local and the, so just.
So
yeah.
the CMB constraints are around 67.
67. So closer to this value, right?
Yeah, but I mean.
Yeah, I know.
Let
me speculate.
Yeah, okay. And the local universe is around 72.
Okay.
72.
Okay. And my second question is, what else do you take into account when you do this? Because you have a lot of other parameters, right? So explain to me, because I'd like to know if this depends on other cosmological parameters that in what you are doing with them.
Okay. So let me show you. Yeah, this.
Yeah, that.
So,
yeah.
So to compute the clustering of to compute the distribution of galaxies, you must account for many parameters. So not just these things right here, right? But the thing is that the other parameters will only change the amplitude of this thing right here. So imagine there's a third dimension here, which is maybe the amplitude of this cross correlation. It will change the shape in this direction, so the amplitude. It won't change, it won't modify anything about the thing that you're seeing here in 2D. That's the main catch here.
Okay, thank you.
Hi, Jean. Can you go to, I think, 27 or something? Like that? Yeah, so this is, so just a simple question. What happened if you just measure a second bright siren? What happens to your, you showed us before that when you include the bright siren, you can get a peak in there. So what happened in this determination with the current data if tomorrow we see a bright siren? What would happen to the precision you gain in your determination of H naught? Will be like really improve a lot, or this method isn't that sensitive to the just jump of 100% in the bright sirens?
No, I don't think it will jump a lot, but yeah, it will certainly improve. So what you're seeing here, so do you see the spread of this peak? So this has to do with the uncertainty that you have in the determination of the distance. Right. So the dark siren has a very poor localization in distance. But you see that the bright siren is much localized because we know we have a very, it's not because it's a bright siren actually. It's just because it was close to us and then we had a.
Right, but if you see a bright siren that is a larger Z, would that help a lot? I mean.
So I think if you see a bright siren at a very high, I mean you could use if you use the redshift as if it's a bright siren, you know the redshift, you can use the redshift and then your constraint will be much better. That's
okay,
true.
Okay.
But here in our case we're not using this redshift information. So in our method I don't think it will get much better, but if you use the redshift information then I think it will get much better. Yes.
Yeah, just remembering that the horizon for kilonovas in LVK is actually very shallow. We don't see very far away. And so we we see something, it has to be close to us, right? As I recall, João, maybe you horizon for a bright siren for bright siren is about not more than 100 megaparsecs or so.
Yeah.
Or something like this, right?
Yeah, yeah.
And the distance error, even for the kilonova, is what dominates that. If you show the plot with the probability for H0 with the kilonova, I think it's one in the beginning there.
Yeah.
Yeah, that one, for instance, right? You see that it's very broad, and that is driven by the fact that the distance measurement has an error of about 25%, even for the kilonova. It's dominated by that, because we know the redshift perfectly. So if you add something more like this, it will be looking, I mean, probably looking pretty much like that.
Okay, so can you go to one of the last plots? I think, yeah, that one.
This one?
That one, yeah. So if I understand correctly, the dark siren is more peaked, right? And the yellow curve is the.
It's the dark siren, yes.
Oh, the yellow curve is the dark siren.
Yeah, and the blue one is combining with the bright siren.
Ah, okay. So I misunderstood because it's the. Okay, okay. Now I understand. Thank you. Oh, because I thought it was the opposite. Okay, good. Thanks. No, it's very good.
Any more questions? I have a silly question. So I noticed that you didn't mention future properties.
Yeah, so the thing about LISA is that they are sensible to, so LISA is supposed to be like this astronomical detector, right? So yeah. So LISA will be sensitive to gravitational waves coming from supermassive black holes. So things are moving very, very slowly. So it has something to do with the size of your detector. So LISA won't be able to detect these high frequency things. They will only be able to detect these very high frequency things, but then it's we won't be able to localize them because they are not these transient objects. They are happening all the time. So what we will detect with LISA is like a background, like a gravitational wave background in frequency. We won't be able to pinpoint where they're coming from.
Is there any other way to measure the A0 from the, because we can measure from C?
Yeah, that's a great question. I don't know exactly. I don't know.
Yeah.
Hello, John. Nice talk. I was really impressed by all the results. One thing I have in mind, that assumption that you had, like the merger come from the most bright region. That was the case for the bright siren, like that one that.
Mm, yeah, I don't know. I don't know. I have no idea
Yeah, I was
if it's
wondering
the brightest
where
in that
that
region.
assumption come from. Like it's.
No, it's just like an educated guess.
Ah, okay.
That assumption, yes, it's just an educated guess.
Yeah, and
but we don't need to assume that for the peak science method. That's another thing. We're just taking advantage of the 3D distribution of all the galaxies and all the binary black holes. So where there's more galaxies, there should be more binary black holes.
And the follow-up question in the provocation as well is, how many events do you need to have a third source of tension?
What?
How many events do you need to have a third source of tension in the Hubble parameter?
Yeah, I mean, if we have a third tension, maybe we should, I think we should have, it really depends on the accuracy that you have on the events, right? For LVK, I don't think we'll be able to say anything about tension because
Today you have like 100.
So yeah, for LVK we will have around 300 objects, but they are all
But you're expecting
terrible.
way more, right?
Yeah, with Einstein Telescope and Cosmic Explorer, we have shown that with only 10 to the 4 objects, we already can have a third tension.
Okay, thanks. Nice.
I think we don't have more questions. So let's thank Joe again. So let's go to the coffee break outside and come back at 2:30. Sorry, 3:30, right? Hi, so welcome back from the coffee. So today's last talk is by Panagiotis Marinellis from Shanghai Tech University. So he's going to talk on one-shell amplitude approach to spinning binaries in GR and beyond.
Okay, thank you very much. I hope the microphone works. Okay, good, you can hear me. First of all, thanks a lot for letting me be here in one of the best cities in the world, honestly. I'm very happy to be back. I apologize from already because I was not able to be full-time in the Christmas meeting that I would love to, because it's a great opportunity to talk about physics and stuff, but I will be very happy to talk all night today. Yeah, that's all. And I will try to not go over time because I heard that there are some drinks. Some person in the audience here was taking ice, was taking a lot of effort to take the ice to, to the place. Yeah. Okay, so I will start. This talk is going to be a bit maybe different from what most people are working on here, so I will try to be as pedagogical as I can. Please stop me whenever you want, interrupt me to ask questions, anything that you want. I will be very happy to answer. And it's mostly on this idea of using effective field theory techniques and scattering amplitude techniques to talk about phenomena in GR, mostly involving about black holes or neutron stars, given the era that we're entering about precise gravitational wave modeling, and see what we can learn, what QFT can learn us, the techniques that we already know and have mastered. This is work with mostly with Adam Falkowski, my supervisor in Paris. I recently moved to Shanghai Tech in Shanghai for my postdoc, and I'm going to do a review of what we have done here, plus some extensions that have been working alone for some work that will be out next year. And so to give you the talk, I will give some motivation. Why do we care about what I'm going to talk about? Then I'm going to discuss how scattering amplitudes that come from ideas from effective field theory can be related to observables in gravity, but not only. And then third, I'm going to discuss scalar vector tensor theories, which are a very general extension, quite general extension in an EFT sense of going beyond GR, to study beyond GR effects. And at 4, I will just flash our results, given the algorithm. I will try to explain as good as I can. And I give some future directions at the end and conclude. Good, so I hope I don't have to motivate, given the previous talk, how important the era we're entering is. We know from 2015 that gravitational waves do exist and we measure them. And we actually measure them pretty well. It's going pretty well, this business. This is from the last update from the run 04 of LVK collaboration, which is a little bit less than 300 events that we have already observed. Mostly of black hole mergers. Some are black hole neutron star and one neutron star merger that we have detected. And this is going to be even better in the future with Einstein Telescope, Cosmic Explorer, LISA, Taiji in China that I was informed recently. So we are entering like a highly accurate, high precision era for gravitational waves. And whenever you have a highly accurate template for something you want to measure, you can also test deviations from that very, very well, which is what we do in colliders. So what is a gravitational wave? For anyone that maybe doesn't know, it's just a wave. So it's just like you see it here. I took this from a simulation from a paper. And you can split this into 2 to 3 sections. So the first one, it's the biggest part of the signal. It comes from the spiral, which is where the 2 objects are getting close together, but they are still far away. So we can do very good approximations based on the relative distance of the problem, which is what people, when we're doing effective field theory, that's exactly what we do. We separate the length scales. And that's why we can use analytical approaches in this era. And especially the PM expansion, which is what I'm focusing on. It's a funny coincidence that my initials are also PM, so I'm working in the field with PM corrections. So it's quite funny. Which is just an expansion in a weak gravitational field. All the objects are far away, so we can do an expansion in the weak gravitational field and get some predictions, which is in contrast with previous approaches, which is the PN expansion with N. This is post-Newtonian, and it stands for an expansion in both G and V over C corrections. So you expand also in the velocity of the objects. Of course, this makes a total sense because we expect that most, if not all, of the events we're going to observe are moving very slowly compared to the speed of light. We don't expect a super relativistic scattering of black holes. We will be very surprised if we see anything like that. Then there is a region here which is called the merger, these bumps. That's when the 2 black holes merge, and here it's strong gravity regime. We cannot do anything else than numerical relativity for the moment, although we have still ideas. And then last is the ring down. It's these small oscillations that fade away. They're called quasi-normal modes, and we mostly use for the moment black hole perturbation theory, although recently progress in amplitude methods again have proven very insightful here. Actually, and becoming even more prominent in this is last work from last month from some people. Good. So I'm talking about scattering amplitudes. So I have in mind having 2 black holes. It could be also neutron stars, anything, that are scattering, and they can have some mass, they have some velocity, some spin, and they are well separated. So the impact parameter of these 2 objects is quite big. I want it to be, how big do I want it to be? Well, I want it to be as big so that I can use my weak field expansion, expanding around Minkowski spacetime. And that means RS is much smaller than B. The Schwarzschild radius of the object has to be much smaller than this B, so that I cannot resolve effects that have to do with the internal structure of the object. Since they are spinning, I can also treat their spin in a perturbative expansion. And in this case, it's some technical thing, but you can check that the spin expansion, in this case, the appropriate scaling is this combination of this classical spin, so this is just a big number, divided by m, which has to be much smaller than b again to be able to consistently do these expansions, which makes sense for astrophysical black holes. So how can we describe this classical scattering process using quantum field theory? That's the main question. And the answer that I have is that is the K-MUSI formalism, which is a formalism that relates scattering amplitudes directly to observables. One mention here, one comment, I don't have it on the slide. Of course, you can ask me, the gravitational waves we observe are bound orbits and not scattering. So what are you doing here? This is not the same problem. You will be correct, but we know that for most of the way we build the gravitational wave template is by building a Hamiltonian for the interaction of the two bodies, and then we insert that to an effective one-body formalism, which is like some technical thing, But the point is that we want to know the potential to construct this Hamiltonian, and then we insert that thing in this effective one body that builds the template. And this Hamiltonian is the same for the scattering and the bound orbit, up to very few caveats, but which are not important. Essentially, we can think it's the same. Okay, so what we measure in the gravitational wave events are waveforms. Especially, this is usually called in GR the strain, and it's basically the leading order behavior in 1 over x of some radiation field. So if I choose this to be the graviton field, I expand this in 1 over r, and the leading behavior is what we measure, and we call this the strain or the waveform. It's a time-dependent object, obviously. It's like a wave that's measured, and in a scattering amplitude sense, this formalism that I was mentioning before, the chemistry formalism, helps us directly compute this object. How does it do it? So the information, we have to think the following, that the event we're trying to cover has 2 massive objects that are colliding, so 2 massive objects that are hitting each other and they're scattering. So 1 and 1 prime is the same, and 2 and 2 prime are the same. And while they scatter, they can also, of course, they can also just scatter and don't just interact through the potential, but they can also emit something, which is actually what we measure. That's what we're more interested in. So they can emit some wave or some graviton. They are in one-to-one correspondence. And in fact, it can be shown that at leading order in this Postman-Coefficient expansion, if you want to compute this waveform, the strain, you just have to take the 5-point amplitude of a theory of massive particles interacting and emitting a graviton, and just plug it in the formula, and then do some integrals, which, trust me, I know how to do, okay? They are not so easy always, but at real level they are trivial, and you can get your answer. So you just compute a 5-point amplitude in QFT language. You take some appropriate limit of the classical limit, which has to do with this expansion. So you are dropping terms related to the scales of the problem, which would give you quantum contributions. You keep the classical value, and you have your waveform. It's as simple as that. This also holds at loop levels up to some caveats again, but basically it holds for the purposes that we're going to discuss here. And you can ask me, okay, why? Why would I do this? Why would I just not use the classical techniques that people in GR are using, and why would I use effective field theory and scattering amplitude techniques to do GR? That's a good question, but I have many answers, and I give a limited set of answers here. First of all, it's a perturbative expansion in a very simple algorithm. You see, like you just have to compute 1 amplitude at loop level, and let me mention that at loop level, this formula still holds up to very few caveats. The point is that the information is, I want to mention that it's only the 5-point amplitude that actually contributes to classical observables. So you would maybe think that, oh, 2 massive black holes are scattering and they emit many gravitational waves. So I should also compute the amplitudes with more gravitons here emitted, but actually no. In these formulas, only the 1 graviton emission is enough. It has all the information. With loop corrections, which is of course it can be very difficult to compute loop amplitudes in gravity with 5 points, but it is an algorithm. The results are analytic. They are stronger than the PN, the numerical relativity in a sense, because they resum information from the PN, which does a double expansion. We don't do the double expansion, so we have resummed infinite orders of these V over C corrections, and this will be very useful in the templates. We can exploit modern techniques we use in particle physics to compute loop integrals. Lately, it's really, we just have to recycle whatever we know, we have learned about QCD integrals, for example, and just plug it in GR, and they are essentially the same. You find the same solutions to a similar problem. And what I want to show here is that you can also straightforwardly extend this to beyond GR predictions, which is very difficult if you're trying to do GR. If you try to introduce fields, additional fields in GR and do some EFT, it's super difficult to compute these extensions, because already the already doing the only GR problem of this is difficult because the GR has nonlinear equations of motion, and to solve them is difficult. Imagine now adding more fields, so you have nonlinear coupled differential equations that you have to solve simultaneously. It's super difficult. But here we can give a simple algorithm on how to do this stuff. Okay, so I'm using on-cell techniques. I will just mention this, but I will not go into detail. These are some techniques that we compute directly the scattering amplitude by using the very basic assumptions of QFT, like Poincare invariance, locality, unitarity of the S matrix, without having to go through the trouble of going with Lagrangians, gauge invariance, introducing the fields and everything. Like, we don't have to do that. We can just bypass all this information and directly compute the amplitude with these techniques. And this is especially relevant. Of course, you can do the same thing and just get the same amplitude. It's fine. But this is especially relevant because for the business, we want to also describe spinning objects, as I said, and it's very difficult. Imagine, try to do a massive spin 2 even object in a classical computation, in standard computation, it's impossible. And here, the black holes, they don't have spin 2 in units of h bar. They have huge number. It is maybe 10 to the 76, I think we calculated in a paper. It's huge. So with these techniques, you just do a redefinition, go to a different set of variables instead of using momentum and polarization tensors, and you basically compute this object very easily. It's just a very smart change of variables, which makes basically, it makes the little group transformations that come from QFT apparent in the last answer. That's what makes them so powerful. Good, and that's an overview of what I want to show you. Don't be scared by this. The important things, there are two important things. The one is this guy here. So I'm showing you here from our paper, if you combine these on-cell techniques with these K-Mosi formulas, you can write, so this is the waveform that I was mentioning. This is really the wave that you will measure at leading order in this expansion. This is in a spin expansion, and I'm showing you only the 0th order in spin. So two Schwarzschild black holes colliding, leading order result. And the result is this line. Of course, here this is some parameterization. Okay, I have chosen some very smart variables about doing integration techniques and stuff. But I just want to show that this is one line. And I will tell you that you can try to go and look the old papers of the 70s and 80s who computed this object at some post-Newtonian order, not even the whole thing. They computed some post-Newtonian order. It takes around 3 pages. So it's really like powerful. Like we're really resumming a lot of stuff, and the information is encoded in smart variables in very few terms. That's the power of these techniques. These are some parameterization variables. They are not important. You don't have to pay attention. I put them for completeness. The thing is that from the waveform, you can also get other observables like the emitted power in gravitational waves. So I should be able to recover the well-known formula from GR. And indeed, I can do that. So I can post-Newton and expand this thing, which basically means take my answer and expand in V over C. I can do that. So you can see the velocity separation here. And I can compute the emitted power by just doing this integral over the celestial sphere and taking the time derivative of the waveform squared. It's some formula that we derived. It's pretty simple, actually, pretty straightforward. And you can compute this thing. So it looks like this is the formula at leading post-Newtonian order. This is for scattering. That's why I have the B over to the 4 here. But I can relate this. So this arrow means that I'm going to the bound orbit case. I told you that most all of the results can be analytically continued to the bound case. And in this case, I can do it. And if you check, you can check any formula. This is the classical GR. This is what you get from, this is what Einstein computed up to a factor of 2, which he got wrong. But he computed like in the 30s, I remember. One important thing that I will mention, which will be important from the thing, you don't have to remember any of this slide. Just wanted to emphasize the simplicity. The only important thing that I want you to remember is that the emitted power in GR at this post-Newtonian expansion is V to the 10 at leading order, which is important for later comparisons whenever you try to modify GR, because you have to check what you are computing is phenomenologically relevant or not. Good. Now let's move to some modifications of GR. I will try, what I'm interested in is the scalar vector tensor theories, which are some effective field theories of modifying GR by being quite agnostic. I'm just going to introduce some extra gauge and extra scalar field, and I want to try to see what are the leading order corrections in an EFT sense, because we have to always keep in mind that I want to try to see if something is phenomenologically relevant here. So I'm going to be like, okay, let's take a generic extension, and let me try to see what this can give me. This U1 field, it doesn't have to be standard electromagnetism. There are many scenarios about this could be a hidden sector like a dark photon. So this is also relevant for people that have been doing phenomenology. I will show you that in these scenarios, actually the results can be quite insightful in this business, and you can maybe even get predictions, good predictions for the gravitational wave corrections. Yeah, so I just want to use the core idea of VFTs, so I will just do an expansion in the mass, in the big scales of the problem, starting work from the Einstein-Hilbert action, adding these generic modifications, and then I will try to see what are the leading order operators in my EFT. That's all. Let's see what this is. So the EFT that I will have, I'm just focused on the massless sector here. There is also massive particles, which represent the black holes here. So there are in the EFT, there are the terms up to these smaller than 4, smaller equal to 4, which are the Ricci scalar, okay, the kinetic term for the vector, kinetic term for the scalar, blah, blah, some scalar self-interactions. That's standard stuff. And then the moment I start going to do my EFT expansion at d equals 5, I find the leading order terms in this expansion, which consist of coupling the scalar to the Gauss-Bonnet invariant, or the Chern-Simons invariants, which are just R squared. You can think of them as R squared. These are the only, independent at this order. Same for the gauge field. You can also couple it to F squared or FF tilde. Again, these are the ones that they are linearly independent if you couple them to scalar. And it happens that this theory has actually already been studied. Probably the people that started it, they didn't know about EFT then, but these theories, they exist. They were coming from storm string-inspired models, and people in modified GR community had been working on them, doing very nice results, getting solutions about these modified theories. Super good. So these things exist. And then of course, I can start building higher order, blah, blah. I can do whatever, I can continue with this story at higher orders, but it's not important. Let's focus on this sector for here. And I will, if we ignore the scalar self-interactions, actually these things have already been tested. So already with the current data from gravitational waves, people have already computed in this paper that was published this year, have already computed the bounds for these modifications. So for the case of Gauss-Bonnet, in fact, the best bound ever comes only from the sample of gravitational waves from the first run, which is, it's incredible that, I was not expecting it, to be honest. I was not so optimistic. But it's crazy that the gravitational wave, the constraints from the gravitational wave for this term is so strong that it overcomes all the bounds. I will explain later why is that. There is an intuitive reason why you get such a good constraint. For the Chern-Simons, this is the best bound, but it's not from gravitational waves. It's from some neutron star observations. The gravitational wave is 4 times bigger, and you can ask me at the end if you want what the reason. There is also an intuitive reason why is that the case. And so we saw that this can be tested. So for these terms, these are a bit more complicated. These type of interactions with a dark photon potential dark photon. So there are not clear constraints. There are constraints on some, there are constraints on the parameter space, but I couldn't find an exact constraint on beta and beta tilde. So there are some combinations of them that are constrained, and I found, and they are also quite broad, to be honest, so they're not very well constrained for the moment. But I'm sure we can do better, and you will see why. Yeah, the biggest constraint comes from they predict some kind of flux, which I will come later. I will come later to this result, actually, exactly, for the dipole radiation. Okay. So one could think to do the most naive thing, to just take this action, compute, like expand in weak field, eta mu nu equals plus g mu nu, plus h mu nu, blah, 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 compute Feynman rules and input, or use my own set techniques, the same thing, and just compute what are the modifications. But you will be missing some things, some stuff that are very important if you just naively try to not think about the problem. And what you are going to miss is the fact that now your black holes are no more Schwarzschild or Kerr. You have modified your GR solution. Therefore, the black hole, the internal structure, secretly knows of the existence of the scalar and the photon. So this is somehow encoded in the new solution of the black hole. And for example, for the case of a scalar, which is the simplest one I can explain, is the fact that there is a solution here that can be potentially hairy or charged, like Reisen Nordstrom and stuff, but it can also have hair in the sense of a non-vanishing scalar field, phi, since if you have the equations of motion for the field phi, you see the gravity sector now sources the phi all the time. And you can, if you go far away from the black hole, which is where we are, because the two objects are far away from each other, you can expand this phi in a multiple expansion, like 1 over r, 1 over r squared, blah, blah. And actually, people in modified GR know what are these. So these are, they have a name even. So these coefficients of the 1 over r terms are called monopole here. Whenever this monopole here is absent, the second one is called dipole here, et cetera, et cetera, et cetera. So there is a long-standing literature on this stuff of people adding scalar fields to describe phenomena that we're interested in modified GR. And the question is, how can I model this scalar here with an amplitude? How does the amplitude know about the appearance of this? And the answer is that you have to try a bit harder. So you have to think that the black hole has some scalar field environment. You can build the most general metric, which is well known from this paper from the 70s. This is the most general metric that you can build in a scalar international theories fashion, which is consistent with causality. And you see it has two terms, a conformal and a disformal one. The disformal is suppressed even more by some scale, so I can neglect it for the moment and let me focus on the conformal. And I will actually check that this is what I'm doing is correct here at the end. And I can, from this term, if you go on the way and do the Feynman rules and see, this produces extra interactions. So it introduces new interactions to the Lagrangian, which actually you can, for all spin orders, we showed in our paper that you can actually just put them in a form where all this information on this C parameter, which is a function of phi, is just redefining the mass. So the mass term, which is phi bar phi, and here the mass is the black hole mass, has an infinite number of interactions, potential interactions with this scalar. And therefore, it's like sourcing it. It's like there is a 3-point vertex with two massive, one scalar, which was not, it is not here. This doesn't exist. Because I assumed that I'm in gravity environment, so I was expecting only massive graviton interactions. And the same thing goes, I don't have time to talk about it, but the same thing goes with the charts. So you can show that in these solutions of this Einstein-Maxwell-Dilton axion theories, whatever, with this f squared and f tilde, you also introduce a new chart, which is now dependent on the parameters of the theory, this beta tilde that I had. So that's the idea. There are induced, which if you didn't know and you were just thinking, you wouldn't know about this, but you have to build a whole solution, the whole classical solution to have knowledge about this. But hopefully in the EFT sense, the good thing is that in the classical limit, only these interactions contribute. So if you do it in a QFT way, these things encode these interactions. let me now do an overview of what I'm trying to say. So in a sense, I wanted to build this kind of object to compute these waveforms. So interaction of massive to massive, massive, massive. I was only having a graviton at the start because I was interested in the gravitational wave. But now I know that maybe there is, if I add more massless particles, this can also be emitted in principle. Therefore, I have to also account for that. And so going back and forth, what I'm doing is the following. I start with some building blocks, this coupling that I have now with this wiggly line represents either a photon or a scalar or a graviton. I have to add all the contributions. And then I have some to find in this Onsel way that I do these 4-point amplitudes that I can build recursively in this Onsel way technique. It's not important. You can also do it with Feynman rules. And then from these guys that can be having like weird interaction with phi, gamma, h, whatever, I can build this 5-point guy and then get the waveform. That's the algorithm. It's very simple. So it's, starting from the 3-point interactions, you build on and go on. That's the idea. And so we want to get information from this guy. That's how it looks for the emitted power. So I did this, and I'm going to show you the result for the scalar, which is the minimal stuff. So the hairy solution with a scalar here has this answer. It looks bad, but trust me, if you try to do it in the standard way, it's much worse. It's really, really much worse. And now you can ask me before asking me, I can do the post-Newtonian limit. I can connect to observables with a similar way that I was doing it before. Okay, and then I see that, the emitted power at 0th order in the spin, it goes as v to the 8. And I told you to remember one thing, that the GR was going as v to the 10. So we see that, first of all, I just want to say that this is in agreement with post-Newtonian results that people have been computing with a lot of difficulty for years through GR techniques. Not only proportionality, I match every factor, everything. I just didn't want to show you here. And that's also the intuitive reason why these theories are so well constrained. They predict a signal which is a dipole radiation, i.e. faster than GR emitted power. So you would really see the two colliding black holes going faster and faster to each other because they lose so much energy by emitting this scalar. And that's why the constraints are so good and so promising. You will notice, if you paid attention to me, if I managed to keep you awake, that here there are some couplings, of course, which I didn't know. Of course, there is always a coupling when I introduce a new interaction. Okay, there is some coupling that you introduced. What is this coupling? So it's this C. I parameterize this C. This is my agnostic way of doing this, of introducing this 3-point vertex. And there is also in this 4-point, with two scalars, there is also another one, even at 0th order in the spin, which I have to be agnostic, and they are here, the C1 and C2 and C1 0. And when we match to the solution, we found what they match to. So this C1 and C2 that I introduced because I was like, maybe it represents, it indeed matches perfectly the scalar here, the scalar monopole charge that people have been computing with very hard in GR. And this is a contact term, which means that it vanishes on the residue of the poles, of the kinematic poles, in the 4-point amplitude. And this also matches to something. It is also another parameter which is independent of the scalar charge, but it appears whenever you have two black hole binaries and they have scalar here. It has been shown in this paper, which have also computed the matching of these terms with explicit couplings of the theory. Because of course, here I'm agnostic, I don't know what they are, and I haven't done the matching, but people can do the matching. So which means, when I say by matching, I mean these parameters that I'm agnostic to, they are related to the Lagrangian of the theory, obviously, the alpha that I had in front of the Gauss-Bonnet and stuff. That's what I modified, so they have to be related. And indeed, they are an infinite series in them. And so I can just plug in the results that people have been computing for these parameters, and then that's how you get the very good constraints on this alpha. Okay, yeah. So what we show, that is the overview of all our results. So let's start. I will start here. Tensor power, GR charge carry. If you start, so this is 0 order in the spin. I should have put it, I'm sorry. This is 0, and the below one is leading order in the spin. So first order in the spin expansion parameter. For GR, and even if you have charge and even you have carry, all these three things for the emission of gravitational waves, all the three exhibit the same behavior. So they are all giving contributions at v to the 10 at the positive 10 limit. So phenomenologically, they are all the same way relevant. Now, if I have the scalar hair that I showed you, for these hairy solutions, I get the v to the 8, which is the enhancement. And if I don't take them into account, so if I was just doing the naive thing of just taking the Lagrangian and expanding, and I didn't take this thing into account, I would never match to GR solution. And not only that, but I would also find that with only from the Lagrangian, you will get a suppression of v to the 22, which is huge. I would be very skeptical whether this would be measurable ever if I didn't have this hair. Therefore, the hair gives you a probe to constrain these theories without directly going through the Lagrangian. So the objects that do not acquire hair in the theories they're very hard to constrain that way. And there is a similar argument. There is an argument for that. We have it in our paper, and why this is so. And there is a similar argument that holds in these theories which have also the charge. So for the vector power, so if they are hairless, basically you can very easily see by counting that the hairless objects that you're going to neglect, and they are very suppressed. But if you have a charged hairy black hole, again, just the charge is stronger than GR again. So it's also v to the 8. Therefore, even if you are searching for this, if you have a model where you introduce a dark sector, you have to be careful if it modifies GR solutions, because if it produces a charge, then this can be also constrained, because it's much stronger than GR. So that's in short what I had to say. Now for the leading order in spin, you can play the same game, and you see that again, hairless, not phenomenologically relevant, hairy phenomenologically relevant, comparing with GR, because GR predicts v to the 12, here I predict v to the 11, so even with spin, this pattern continues. I'm sorry I didn't finish it, but I'm working on it one-man power, so I haven't yet finished the leading order of the spin for the vector and the tensor power, but I expect same orders of magnitude, like the same pattern will continue. So a bit more suppressed with spin, but still more phenomenologically relevant than GR. Okay, I'm done. I just want to give an overview. So the conclusions of this is that these new QFT effective field theory techniques that we have for computing stuff in GR can uncover a lot of stuff about gravitational black hole physics, especially in the context of gravitational waves. And if we want to talk about spinning binaries, this becomes trivial in these on-cell amplitude techniques. And I want to advertise them because I would never be able to do spin without on-cell techniques. I mean, I could, but it would be very difficult. But it saves my life. This can make the search for beyond GR much easier to handle, much more consistent. It's an algorithm. And we have shown in these papers that all these results that people in GR have been very hard trying to compute with traditional methods, they almost trivialize. I mean, they become a part of the algorithm. So they are much easier to compute. So all the discussion was perfect and was everything good, but I don't want to oversell what we have done. We still haven't matched the dipole here. So if the leading order in 1/r contribution, if you remember that I expanded this classical potential of the phi in the far zone that had 1/r, 1/r squared terms, the dynamic Simons theory, the one that with alpha tilde, actually has dipole here. It doesn't have the monopole here. There is an intuitive reason for that I can explain. But we still haven't managed to find how you can. We've been pretty close in our paper. We found some pattern but we match a part of the answer. We don't. There are two terms in the answer of the classical GR, and we get only one of them. That's the short explanation. And so still, it's an open problem that it looks very promising, and no one has ever computed beyond very leading order in this theory because it's super difficult. So it would be very interesting if we could get results for that from an amplitude perspective, because it would trivialize the problem, and no one knows how to do that. Then another question is, okay, can we use these frameworks to study other beyond GR effects with scalar particles, for example, like boson clouds around black holes are an interesting avenue that I'm currently a little bit interested in and thinking about. Soliton and boson stars. Actually, there is a paper that I got yesterday. It went to my attention. I'm sorry I didn't put it in the slides, but some people do it with similar to amplitude techniques. Yeah, then maybe you can have some light action particle. There are many ideas that you can apply this framework for beyond GR. And the last is, okay, you can also ask whether what I wrote makes sense. It's an EFT, but a good particle physicist should always ask whether I can complete that theory. And actually, we also had a paper that is, I think it's already accepted in JHEP, so it's going to be in the published version in the next days. That we tried to compute these interactions to find some general UV, to find the most general UV completion of theories of that sort by only introducing the simplest thing you can do, just 3-point couplings of massive matter. Here, this massive matter is just higher particles that we haven't yet detected, that they can couple to the graviton and the scalar. So this would be the Gauss-Bonnet or the Chern-Simons theories. And again, we computed them for 0 and 1/2 and spin 1, which was very good using the Onsel language again. And from the UV, this appears in the UV, and in the IR, where these massive particles, they have bigger masses than what we measure. And currently, they give you the Gauss-Bonnet and the Chern-Simons theories. And for example, we found that the Gauss-Bonnet theory, it generates a whole host of operators in the EFT, which look to have nothing to do with each other. So people that have been computing classical GR solutions to these theories, maybe they should add more terms to the EFT expansion because they are actually predicted. So maybe they're losing the correct classical solution for the black hole. And in the Duncan-Simons, an interesting thing is that we found that there is a unique way to keep the shift symmetry of the interactions, the phi RR tilde. And this is related to axion physics, which you maybe know, that this corresponds to the spin 1/2 fermions, and you have to add a complex scalar with a Pichet Queen, the well-known global symmetry for the axion models. And this is actually unique if we show that this is the unique choice if you want to keep the shift symmetry of the theory in this case. And with that, thank you very much. I hope, last thing I want to mention, I took this amazing picture from, this is an artist that spent 1 month in a university with a particle physicist that does collider physics and an astrophysicist. And this is the result of the 1-year visit. So I hope this really, I don't have to say anything about that. This concludes my talk. Thank you very much.
Thank you, Panagiotis, for this wonderful talk. We can have some questions now.
Hi. So you started talking about the limits that you have, which are, you mentioned, mainly coming from the first run of LVK of LIGO.
Yeah.
How they connect to these calculations that you've done here? Are they also using a perturbative approximation, or they are in a regime which is, we don't really see a lot of, we don't see a long waveform. We see typically with LIGO at present, we only see the very end of it. We see a bit of that waveform. So I would suppose that limits are coming really from the almost non-perturbative regime of that waveform.
Yeah.
Right. So and you're talking here about more the perturbative regime, right? So we would need to see a very long waveform in order to use these calculations to put constraints on these parameters. Is that correct?
Almost. So it's almost correct. In fact, what they do is they do a showing. So actually, the people that do this paper, oops, what did I do? I'm sorry. I don't know what I did. The people that do this paper, they are also the people that have introduced the effective on bodies group in Berlin. So they mostly do the perturbative regime, so in spiral, and that's what they were proficient in. What they, from my understanding, not from my understanding, but this is what they did. They shoot the results from the spiral that they knew very well, but they only have the post-internal results that some people all knew it in the literature in these last years. So they shoot the results from the in spiral with some numerical relativity simulation, I think, from the merger, and then some stuff for the quasi-normal modes, I think. And then they got these results, but it is not clear from the paper how much of importance it's from the one or the other. However, I have to mention that so actually we saw in our paper that these things are measurable from the spiral. They are measurable. You can just power count, and you will see it even only from the spiral. Not only that, but there is a very high possibility that you cannot even use these theories for the merger and the ring down. And the reason is that these theories, they are already very hardly constrained from causality bounds. So they violate causality in some regimes. So if you try to, already there is a paper which they say that they have excluded completely using it for merger and ring down. For the merger then, for the merger. If you want, I can give the reference. So the inspiral is the only where we are 100% of what we are doing, and we have control of the EFT expansion. Yeah.
Hi, thank you. Just a question for clarification. When you talked about the extensions, for say scalar or vector extensions, you said the case of the hairy cases will be very constrained because they are stronger than gravity, right?
They are, sorry?
They have this power spectrum is bigger than. So what you mean by hairy is it will have just some charge, basically.
It will have some scalar charge, and if you have
some global symmetry or some scalar charge. So your theory, your extension will have some global symmetry, some global charge.
No.
Specifically, you know.
In fact, no. In fact, it's the opposite of that. Actually, it's the hair. The effects related to hair are actually, you can think of them as spontaneously breaking of a symmetry. For example, in this Gauss-Bonnet, forget about the other operators, just Gauss-Bonnet, which is the most studied. These theories are shift invariant over the scalar field phi because Gauss-Bonnet is a topological term in 4 dimensions. And if you add the scalar charge, you can show, and we show, that it actually breaks the symmetry of the theory.
Right. So this is a charge. The scalar is charged, and so this is symmetry breaking.
Yeah.
And so that's the condition for you to have to screw up basically eventually the power spectrum.
Yeah. Exactly. Yeah.
If your dark sector does not get your scalar, for example, doesn't get a VEV, what would happen in the vector sector? The vector, what would mean a hairy theory for touching the vector sector?
Mm-hmm. So for the vector sector, so first of all, if you introduce just a random vector with no other interactions, already you know that there is a possibility that you will have charged solutions. If your normal matter, if the black hole is created by normal matter and this normal matter is somehow charged.
No, of course.
Yeah, but if you have these interactions, for example, this phi with it has been shown that it gives rise to both scalar and charge.
No, that I see. So you have to have the scalar and the vector. Okay.
No, you don't have to. Also, if you add even if you don't add the scalar, you just add an extra vector, another dark sector, then if you know that this couples to the Einstein-Hilbert because there is a square root of minus g in front of the fold action if you have gravity. Therefore, if the matter that created the the charge, if the charge is conserved,
Okay,
then
okay,
the matter
okay.
that created the black hole will
right.
give a charge to the black hole.
Sure, sure, sure. Okay. Thank you.
Do you have any more questions? Okay, so if you don't have any more questions, let's thank him for. So we go now for the drinks or after some time? So we go to the main building for the drinks.